We are going to cover the sampling and center limit theorem, right? In the previous sessions, we discussed the importance of stats in real life, centering spread of the data. We discussed the probability, starting with its history, conditional probability, and random variables. And we saw what were the Bernoulli trials. We saw distributions, the normal distribution, and set transformations. Starting the sampling. By now, we have studied about or talked about many experiments using coins, dice, and some abstract ideas. Now, how is it relevant in the real world? Now we are going to find out actually. And in this chapter, in the session, will begin looking at the real business of stats. Why? What is the importance of stats in our real life? How do we implement it? Right? And the objective is again to save people time and money. Okay, this has been the objective of humankind since the start. Whatever researches have been done are to save time and money because as we progress, we have lesser time and more money. Okay, so we want to save both of them, and we obviously want to avoid doing unnecessary work, right? So let's see how stats can help in saving time and money. In the real world, the problem is that the collection of stuff in it is so large, right? So it is very hard to get the information we want. For example, if I ask you, what is the average age of human beings on Earth, right? So there are almost, more than 8 billion people on Earth. You can't go to every person and ask their age and then take an average, right? That's a very big exercise to do. So similar examples that you see here, one is, let's say, voting populations, what percentage favors each candidate. You can't ask every one of the person who has voted, right? Which candidate do they support, right? So same way, if a factory is manufacturing some goods, how much proportion of the goods will be defective? You can't look at every product and test if it is defective, right? So you use stats over here. Next example for pickles, let's say there's a factory for which makes the jar for the pickles, and they need to know the average length of the pickles. So obviously they are not going to measure the length of every pickle and then find an average. So what they use is statistical techniques. Um, Again, they are saying the same thing here. We can't be using the manual approach to measure or to measure the length of each and every pickle which is produced out of the factory, because they may be in billions. At a month level, there may be billions of pickles being produced, right? So you can't measure the length of everyone. So what we do is we get statisticians, right? Because we can't do the manual work. So to overcome this, we have one method called sample. Okay. In sample, what we do is we take a relatively small subset of the total population, and all the people who are coming for surveys and all pollsters, they do it all the time basically, right? So instead of surveying the whole population, they will survey only a particular set of people that they have already selected using some sampling techniques. Again, one obvious question that would come here is how big a sample do we have to take to get meaningful results, right? So obviously it has to be greater than one. Now, also, how do we know how much should be the number of items in the sample, right? That was the question. So here comes a very magical factor of 1 by root n. We have seen this many times, right? And it's a very important factor. You should always keep this in mind, right? And if n is the number of items in the sample, then everything will be governed by 1 by root n. which we'll see in the upcoming slides. Now, before going to the numbers more, let's talk about the quality of the sample, right? Because it's as important as the size. And how do we assure ourselves that we are choosing a good sample or a representative sample, right? So basically, we want to know if our selection process is good enough or not. If it's not good enough, then we can't infer anything about the population, right? For example, in a selection process, it may be biased towards certain people or certain group, right? For example, it may be systematically excluding black people, or people based on caste, right? So that is what brings in a bias in my sample. So how do I make sure that these selection process is good? The best way is to choose the sample at random, right? Uh, I mean, as an example, what you can say is this is the pollster, and how he's choosing the random variable is he has just kept a blindfold on his eye, and he's pointing out the people, uh, and whoever comes, I mean, he just calls out some numbers maybe, or you can also call it as a lottery system basically, right? So this is the random sample, and this is the best sample. Again, putting a definition to it, this is the simple random sample, and in this, all the objects, they have a equally likely probability, and then only we can call this procedure a simple random sample, right? Now let's look at the properties of simple random sample. It should be unbiased. Uh, that is, each unit has the same chance of being chosen, and it should be independent also. So selection of one unit should have no influence on the selection of other units, right? If these two criteria are satisfied, then we have a simple random sample. But unfortunately, in the real world, which is so-called unbiased, right? Independent samples are very hard to find. For example, surveying voters by randomly dialing telephone numbers is biased, and the reason is because every voter doesn't have a telephone number, right? So that is biased. Now, to overcome this, we have certain sampling techniques. The first one is stratified sampling. In this, we divide the population units into homogeneous groups, which are called strata, hence stratified, and then we draw simple random sample from each group. Okay. So, for example, for the pickle example, let's say we divide them into garlic dills, uh, pickled peppers, kosher dills, and so on, right? So these will be the strata, and then when in every strata, if I do a simple random sample, I will have a stratified sampling. Second is cluster sampling, in which the population will be divided into small clusters, and within each clusters, a simple random sample is chosen, right? For example, if we are doing a survey in a city, housing survey, let's say, so we will divide the city into blocks, right? Which can be uh, block A, block B, or so on. Then we can randomly sample the blocks and look at every housing unit in each sample block. So this is cluster sampling. Next is systematic sampling. The systematic sampling, in it, what you do is you randomly select some item, and after that you select every other kth unit thereafter, right? So for example, if you observe the color of the car, right, randomly at once, and if you observe the color of every 100th car from that car, so that will be systematic sampling. Next is opportunity sampling, right? um, I mean, this is again very biased, but this is again a highly used technique. And what we do in it is uh, the sampler just grabs the first 8 population units which can come along and draw the inferences from that sample itself. So that's why since it has top people, or basically first in the queue, some logic they may have, right? So this can be a biased approach as well. Now let's get down to an example of brass tacks. Okay, let's say we have a factory which manufactures brass tacks, and these brass tacks can be defective, right? So we call the factory as Bernoulli Tag Factory, because it's again Bernoulli trial, in which the probability of not defective is, let's say, P, right? But some would be defective inevitably, right? It is for sure, because no machine can produce a 100% correct output every time. Now, again, when we say it's a Bernoulli Tag machine, Bernoulli Tag factory, we can, I mean, the reason we say it as Bernoulli Tag factory is we can find similarities with the Bernoulli system. Each new tag has an outcome of is an outcome of Bernoulli trial, but and some probability P of success is there, and probability 1 minus P of failure is there, right? So it's a binomial, right? Um, we can think of this situation as a Bernoulli machine, something at the back, right? Whose probability P governs the outcomes we observe in the so-called real world. Okay. Now, in real life, since this machine is invisible, so we don't know what P is, right? So what we do is we take a random sample of n tags, and we find that X of them are okay. Let's say we find X of them are okay. For example, if we take 400 tags and we find 352 are okay, then we can calculate the proportion of the success. Again, the proportion of success in the sample, it has to be somewhere around P, right? So we call it P hat. So P hat is the proportion of success in the sample. So P hat will be X upon N. Now P hat is the number of successes N X in the sample divided by N, which is the sample size. For example, if small p is 0.85 and we sampled N is equal to 1000, then uh, maybe we would have seen that 832 out of them are good, because obviously your P hat is 0.832, right? Now, if you see here, your P was 0.85 and your P hat is 0.832. They are very close together. So that is what they're trying to say. Your P and P hat will be very close. Now, the next question would come is how do you know if your estimate is very good? So, again, we take a step back and then we see what does goodness mean, right? We should have a parameter. We can't exactly know the difference between exact difference between p hat and p, because we don't know the value of p. We can never, right? For population we can never know this. That is the reason why we do sampling. So the real question now is, if we took many samples of 1000 tags and observed p hat for each sample, how would they be distributed around p? Now I think we are converging on the goodness, right? So we want to know if we take many samples and we observe p hat, basically probability of defect or probability of good for each sample, how would they be distributed around population mean or population probability, basically. In fact, these all p values are looking more and more like a random variable. The selection of any sample is a random experiment, and the observation p hat is a numerical outcome. When we select the n-unit samples, it becomes a random experiment, and the observation p hat is a numerical outcome, right? So, to be precise, if capital X, let's say capital X is the number of successes in the sample, then capital X is nothing but it's a binomial random variable with n trials and probability p. And we have already defined the observed proportion to be random variable p hat, right? So we define it actually. So capital P hat will be capital X by n. Big P hat, capital P hat is the random variable, whereas small p hat it's the value for a particular sample. Now, since we know all about capital X, we conclude a few points about capital P hat. The mean of capital P hat will be small p. Okay. The standard deviation of capital P hat is going to be uh, under root p into 1 minus p upon under root n. So this again, this denominator under root n or the magical factor of 1 by under root n, this again comes here. Please note this. When the n gets large, p hat is approximately normal, right? So p hat will tend to normal once n gets large. Now, the observed values of p hat will be centered on p, right? And their standard deviation or spread is proportional to the magical number 1 by under root n, which we already saw. So please note that this doesn't depend on the population size. It only depends on the sample size, right? Now, since a p hat, a capital P hat is nearly normal, we can use the rule of thumb to conclude that approximately 68% of all estimates they are going to fall within one standard deviation of the true value p. We go back to the tax, right, and say we have a small n of 1000, that is, we take 1000 tax, and we already know small p as 0.85, and so we get a standard deviation of sigma p hat, capital P hat is under root of 0.85 into 0.15, which is 1 minus 0.85 upon 1000, which is n, right? So this is 0.0113. So what we say is that capital P hat has a standard deviation of 0.113, meaning we would expect about 80%, 68% of our estimates to fall in the narrow interval of 0.8387 and 0.8613, which is sigma plus mu, sigma plus mu, mu plus sigma and mu minus sigma. Upper value is mu plus sigma, lower value is mu minus sigma. Right. So if you plot it, it will be something like this. It's a coincidence basically that this actually matches with the shape of the tag. Moving on. Also, let's talk about the sampling error. So for sampling error, we just measured the standard deviation of capital P hat and we call it the sampling error, right? As we have already seen that for the binomial capital P hat, the sampling error is inversely proportional to under root n. When we increase the sample size by a factor of 4, our standard deviation will reduce by a factor of 2, right? So that is again one inference because it is inversely proportional to root n. All right. So in this table as well, we have sample sizes for tags. P is equal to 0. P is already, we already know it. So for example, if n is 1 capital under root n, this is under root n. If you see, it increases as you move from left to right. And your standard deviation, this decreases, I mean, by a factor of uh, under root n, it will reduce to 0.0036. While if you had only done 4 samples, then it would have been 0.1785. If you do 10,000, if you take out 10,000 samples, it's going to be 0.0036. Now, just a difference between the estimate and the estimator. Okay, an estimate is a single measure or observation, like 1, 2, 3, so on and so forth. An estimator is a rule for getting estimates, right? So in this case, the estimator is the random variable capital P hat is equal to capital X by N, right? So that is my estimate. Moreover, we have already seen the four-step process, right? Let's just reiterate it. We define the population with unknown parameter small p. We find an estimator, its theoretical sampling distribution and standard deviation. And how we calculate the standard deviation is sigma p hat is equal to square root of p1 minus p upon n. And the expectation of capital P hat is p, right? And after that, we draw our random sample and we find the estimate. Okay, so let's say this guy has already found it out to be 0.84. Then after that, you can just report it with a sampling error. Sampling error is basically a standard deviation, right? So this guy has reported it to the senior, but they want to know if the results are good, right? So which is actually the case a lot of times, but that's fine. Um, so we already know, by this time we know that how we can do the sampling, do we how is the probability from the sample going to be normally distributed, and if n tends to be a very big number, this would tend towards a standard normal distribution. Basically all the probabilities of the samples, they constitute a they constitute the values of a random variable. And if n tends to a very large number, your sample itself is going to be a uh, very close to a normal distribution. Again, coming back to the jar manufacturers, they want to know the average length of the pickle without examining every cucumber in California. So what they do is they randomly select 10 pickles and measure the lengths. Okay. By now, I mean, we already have the idea that xi is a random variable, the numerical outcome of a random experiment. Right? Let's say mu is the unknown mean pickle length and sigma is the standard deviation of the pickle length distribution. Then the expectation of xi, capital Xi, will be mu, and the standard deviation of xi will be sigma. Right? We already know that xi is a random variable. So expectation xi will be mu and sigma xi will be sigma. Obviously, this will be for every I. I is your sample. I hope by now we can say that we know a bit more about random variables than we did in the last session. Now we look at the sample mean, right? We took the average of all the selected pickles average length, and we have a new random variable which is given by capital X bar, x1, x2, x3, so on, divided by n, right? Now we would like to know how close this will be to mu. Okay, meaning if sampling were done many times, what's the distribution of capital X bar, which is your sample mean? Because we know about capital X1, X2, and so on till Xn. We also know that expectation of X bar. So this is the expectation of X bar. This is going to be mu. And the standard deviation in X bar, your sample mean, is going to be sigma upon root n. Once again, we see the magic denominator 1 by magic denominator or the magic number 1 by root n. The spread of the observed sample means goes as 1 by under root n, right? The variances of xi upon n add to give the variance of x. So if you try to add them, right? Uh, so this is standard deviation. If you do a square, you will get it variance upon n. Once you add all of them, this n, I mean, this will go away, and the variances are going to be summated basically. Now, we don't know the shape of x's distribution. Okay, we know that capital X bar is a random variable, but we don't know the shape of its distribution. The sample probability distribution we had was almost normal, right? The sample probability distribution was almost normal because it was based on binomial random variable. But what about X? The sample mean estimator. Let's see. Here comes into picture the central limit theorem. So what it says is that it turns out that capital X bar is also approximately normal. This famous result is called central limit theorem, right? Do you remember the bell-shaped curve that we had discussed earlier? So this is the same bell-shaped curve here. It says that if I take random sample of size n from a population of mean mu and standard deviation sigma, then as n gets large, x bar approaches the normal distribution with average with mean mu and standard deviation sigma upon under root n. Right? I will read it again because this is a very important theorem. If I take a random sample of size n from a population of mean mu and standard deviation sigma, then as n gets large, x bar approaches the normal distribution with mean mu and standard deviation sigma by under root n, right? And the probability of x bar between a and b is going. I mean, if you apply the Z transformation here, it is going to be probability z between b minus mu by sigma by root n and a minus mu by sigma by root n. This is the central limit theorem. Um, I think we'll cover a bit of t distribution in a bit, but let me show you a working example. So, in this, let's say there is a surveyor or a pollster, and what they are doing is that they are taking samples, and they want to ask the age of the people, age of the person they are surveying. So every sampler, uh, I mean, they are at once they are taking a sample of 10 people, and they are calling it as sample ones. Let's say S1 and then S2 and then so on. So central limit theorem states is if this n is 10 here, right? If this n is large enough, then this distribution will be very closer to a normal distribution, and the mean of this will be mu, and standard deviation will be sigma by n, right? But the condition is it cannot be exactly the same. It will approach towards a normal distribution, right? Now, what I did was I plotted the so in the column A, you will see the sample of the mean of the sample. Sorry, so the mean of the sample S1 is 39.2. Let's say, so here we take an average of all these numbers and so on, and all of these are random. Okay, but once you plot the sample means in a histogram, this is the histogram that you get. Now, does it give you some idea of which curve is it very near to? So I think your answer should be bell curve, because it is getting approximately equal to the bell curve or approaching it. So if I increase the n here, right, the number of samples, uh, give me a minute. So here, the number of samples that I've taken is 1000. Now, central limit theorem, sorry, my bad. I confused the uh, records in the sample to the number of samples. But what central limit theorem states is that if your number of samples get large, then your this graph, which is this histogram, it will approach to a normal curve, right? So in this example, the number of sample is 1000, and you can see that it is very close to a normal curve. If we want to check it, I mean, you can do it in Excel maybe. You can try increasing it to 1 lakh, and then you can see that what is the shape of the sample means. You will definitely see that it's very close to a normal curve. Okay, so this is what I wanted to show you. Uh, After this, we will just introduce t distribution once, right? Uh, so this t distribution was published by a scientist with the name student. That was it's called t distribution. But the theorem that we have seen, the center limit theorem, it has at least two problems, right? It depends on the large sample size, and to use it, we need to know sigma, the standard deviation. But we don't know it, right? We don't know the standard deviation of the population. So sample sizes are often small, and sigma is usually known, right? So in the case of pickles, we have no idea how widely their lengths vary around the average, which is basically your uh, standard deviation. So we don't have an idea. So that's why t distribution comes into picture. So I won't be covering t distribution a lot, because of some time constraint. Um, but do let me know if you have any questions on the t distribution. I can take them up and we can discuss this as we have the availability. Um, just a bit of formulas. I will show you. Okay, we can what we can do in this case where we have very limited samples is we can estimate sigma by taking the standard deviation of the sample. Okay, let's say we take a sample. So the standard deviation, as we saw earlier, is given by 1 by n minus 1, right, is equal to sigma of xi minus x bar square. So this is not standard deviation, this is variance. Okay, and this is given by this formula, right? I think that something is missing here. There should be variance, right? And in place of the random variable, we take the z transform. Basically, using the z technique, we take z is equal to x bar minus mu upon sigma by under root n, and we substitute small s for sigma, and we define a new random variable t by x bar minus mu upon s by under root n, because my sigma would become this, right? So that's why I substitute sigma in here, and t variable t is given by this. Okay, so this is how we can get a t distribution, right? So do let me know if you have any other questions on t distribution. I can take probably another session, smaller session on that. But this is it for now. Um, I hope this was interesting. Thank you.